Okay, today we're going to be talking about a particular sort of nucleophilic addition that carbonyl compounds, that's aldehydes and ketones, that they undergo when they are attacked by amines, primary and secondary amines. You actually form different products in each case. One thing that you'll have seen already is that whenever you have nucleophilic attack at a carbonyl from a neutral nucleophile, this would be an example of a neutral nucleophile, you usually end up with some sort of elimination of a small molecule in your final product, and these two reactions that we're going to see are really no different to that. So I'm just going to guide you through the reaction here. It is a few steps, and so for that reason I may need to use a couple of screens to illustrate all of the reaction steps here, but I want to go through everything. One thing to note, all these steps are reversible. You can go back all the way to the end and all the way back to the start and all the way back and back and back and back and back. So like I said, these are all reversible steps. And in case you're wondering, I have primary amine written here simply to indicate the fact that this is a primary amine. Okay. Notice the product that we form is a functional group you may or may not have seen before, something called an imine. We'll see how we get to that as we progress through the mechanism. So we have our nucleophile with its pair of electrons, and we have our carbonyl. You've seen already where every single nucleophile will always attack in a simple carbonyl group like this, and it's always right at that carbonyl carbon, the most electrophilic part of the molecule. Okay. So now for each one of these steps I'm going to be drawing out that equilibrium arrow. So let's see if we can draw out what our product actually looks like. We've formed our O minus here, and at this point we have our nitrogen that's formed a bond to that carbon, but already had 3 bonds to itself. So right now that nitrogen has a formal charge of +1. So we have both of these atoms that have a charge, and so something's got to happen between these two to make them happy. Now, there is a reaction that actually happens between these two that allows both these atoms to become happy all together. This oxygen has 1 bond too few and it wants 1 more. This nitrogen has 1 bond too many and it wants 1 less. So the ideal situation would be where this oxygen grabbed the hydrogen from the nitrogen. And that actually can occur. That reaction is called a proton transfer, PT for proton transfer, where literally you have something like this happening, where the oxygen grabs a hydrogen from the nitrogen. All right. So forming a very similar product to the one you just had, except the one that has no charge. And in which case your molecules are a little bit happier, or your atoms are a little bit happier. So let's see if we can just finish off drawing this out again. So now our nitrogen is all happy. It's got its 3 bonds. Okay. So there we go. There we go. Now we are still quite away from the product here. We also have usually a little bit of acid lying around in here, and I'm going to illustrate that just by showing some hydronium here, H3O+. Okay, so let me just draw this out. And if we have that, bear in mind all these reaction steps, like I said, are reversible, so they can all go back the way that they just came. We are going to have our oxygen electrons going out and grabbing a hydrogen from that acid. Now notice what happens to our product once we do this. All right, I'm going to draw this out again. Everything else looks the same, except the one thing that's different now, of course, is that our oxygen is now protonated. So it actually looks like this. OH here, and we have an extra hydrogen there, giving us this. All right. So we've actually turned this alcohol into an OH2 plus, and whenever you've seen this before, you've seen that means, you know what, that is now a very good functional group. So how could that leave? If we've just made it, how could that OH2 group leave? Well, could leave by itself. Something could actually help it kick it, to help it kick out. And actually that's something that can do that is the pair of electrons on that nitrogen. So literally these act like a pair of arms shoving that OH2 out of the door. The electrons go into that carbon-nitrogen bond, forming a double bond, and making this OH2 group leave. All right. Remember I said this was a good few steps here. So before we draw the product out now, you can see, or you're going to be able to see what we've done, is that at this carbon we've kicked off the oxygen. So we appear to have lost a bond, but we've gained a bond by the fact that we've formed a double bond between the carbon and the nitrogen. So in other words, our nitrogen is going to have one too many bonds again. So let me draw this out. Now I'm just going to show the nitrogen up like this. So nitrogen here, okay, there's the hydrogen, there's the R group. Now, what are we missing at this point? Well, what we are missing is a charge on that nitrogen, because the nitrogen wants one bond less. So look at this, and then look at the imine final product. What's different? Well, you can see the only thing that is different is the fact we have a hydrogen that we don't want here in order to get to our product. So something is going to remove that hydrogen. Now, what do you think that something might be? Well, that something is actually just the water that you took off. So, let me just draw that water out. And let's just see what happens. The water says, okay, I'm going to act as a base, grab that hydrogen, and kick those electrons onto that nitrogen. In doing so, I'm going to form some H3O plus that I had before. And there we go. And that is how we get to our imine. And notice we were able to do that because of the presence of this hydrogen here, because this hydrogen could get removed, allowing us to form our imine product. All right. Now that's a primary imine. And so you might be wondering, well, okay, what about a secondary imine? Why does my product here look different than my product here? Here I have an imine, a carbon-nitrogen double bond. Here I have something called an enamine. Enamine because a combination of an alkene and an amine. Why are those products different? Wouldn't the mechanism be the same? It's an amine and a carbonyl. Well, actually, the fact is, yes, the mechanism is almost step for step identical. There is one little place where the mechanism differs a little bit, which accounts for why the product looks different. But let's just go through. You'll see the mechanism, at least to begin with, is indeed exactly the same as it was for the primary amine. Okay? Where literally all that happens to begin with is that the amine acts as a nucleophile. Alright? Kicks the electrons up onto the oxygen, gives the nitrogen its fourth bond, so the nitrogen is positively charged, the oxygen is negatively charged, and you do that proton transfer. I'm going to miss that proton transfer out here just to save a little bit of time. So we have our OH, and then down here we have our nitrogen. Now that we've lost that hydrogen from our nitrogen, we have this. Okay. And it was at this point, once again, like we saw before, that we had a little bit of acid around. And it's exactly the same here. the oxygen from the alcohol is just going to go and grab a hydrogen from that acid. It's very freely available. And grab that, kick those electrons onto the oxygen. Okay. Let's see what we get here. So once again, all we've done is protonate that OH group, turn it into a great water leaving group. And just as we saw for the primary amine, the nitrogen says, you know what, I'm going to give you a little bit of help. I'm going to help you on your way to kick you out of my molecule. I'm the boss. I say what goes. So the nitrogen says, okay, yippee-ki-yay, there you go. Those electrons go into there, form that carbon-carbon double bond, and kick out the oxygen. All right. Now let's see what we get in this case. Last time we got a carbon-nitrogen double bond, and well, we formed exactly the same thing here. Up to this point, the mechanism is literally exactly the same as it was last time. Exactly the same. It's actually, though, at this point where things get a little bit different. We now have our positively charged nitrogen again, just as we had before. All right. Now, the difference here is when we had our primary amine, one of these two was a hydrogen which could get removed to form our product. You can see neither this nor this is a hydrogen, so water can't be removed to remove either of these. But our nitrogen wants a way to lose that fourth bond. It's just not happy. And if you look at the product, you'll see the nitrogen indeed here has lost its fourth bond somehow. We still have a water line around here, so I'm going to draw that out. So what is it that must be removed to go to our final product? Well, to do that, we have to look at this carbon, because we found a double bond between this one and this one. On here is a hydrogen atom. Now, this hydrogen atom is actually relatively acidic because of the presence of this carbon-nitrogen double bond, and we'll see why here in just a minute. This water can actually grab that hydrogen. Now, water is usually nowhere near a strong enough base to do this, but in this case it is, because this hydrogen wants to leave really quite easily. And the reason for that is this carbon-hydrogen bond can break very easily and put the electrons into that carbon-carbon bond, which can then funnel electrons up onto the nitrogen. Normally, water attacking a hydrogen that has no way to do this, that hydrogen is just nowhere near acidic enough. Because of this carbon-nitrogen bond, that is acidic enough, and what we end up with is the way to make a product. We form the carbon-carbon double bond between these two carbons. We've got rid of that double bond here to give our nitrogen its 3 bonds back, and that is how you figure out the enamine or imine products from nucleophilic addition of amines to aldehydes or ketones. So you always want to look out for, am I adding a primary amine or a secondary amine, because that will determine, before you do anything else, if I form an enamine, imine, or an imine product. So primary amine goes to imine, secondary amine goes to enamine. Thank you very much.